Welcome to the 14th lecture of Control System 2. So we were discussing about solution of linear time invariant state equations, and the contents of discussions we have fixed to discuss the introduction, solution of state equations using Laplace transform approach, solution of state space equation time domain approach, and solution of homogeneous state equations, computation of e to the power at, properties of state transition matrix, solution of non-homogeneous state equations. So in between all these topics, last lecture we have covered up to the solution of homogeneous state equations and some methods to compute the e to the power at or the state transition matrix. So today we are going to cover rest of the things. We will study the properties of STM, and at last we will study the solution of non-homogeneous state equations. So last class we have seen that if a homogeneous state equation is there, homogeneous state equation indicates that the output of the input of the system will be equal to 0, and it will be represented by the equation x dot equal to ax and y equal to cx and the initial conditions. Now if we want to solve this state equation, then we have come to know that the state equation solution, that x of t will be equal to e to the power at x of 0, and the output, if we know the state of the solution of the states, then also we can compute the output yt, that is c into e to the power at x0, where the e to the power at is the state transition matrix, and it is nothing that is Laplace inverse of Si minus A inverse. So now we have come to know that if we want to compute the system states at any time t greater than 0, then we have to know the initial condition. Along with that, we have to compute e to the power at. So as I have mentioned that there are several approaches exist to compute the e to the power at, and some of the methods we will discuss in the course, and we have indicated that the methods we will discuss, that is Laplace transform approach, and then we will discuss the Cayley-Hamilton theorem and the diagonalization approach. So in between that, already the two methods we have discussed, and one important thing we have observed, that suppose if we have a system whose eigenvalues are real and distinct, then we have found that the e to the power at, which is also a n by n matrix. Here for this example we have taken a matrix is a 2 by 2, so then e to the power at is also 2 by 2, and the most important thing is that the elements of that matrix, if you see each of the elements of e to the power at, they are some constant into e to the power minus lambda it plus, means lambda 1t plus some constant into e to the power that is minus lambda 2t. So the power of the exponentials are the eigenvalues of the system or poles of the system. So as I told you, as I mentioned, that the elements of e to the power at basically going to determine the stability of the system, internal stability of the system. So this observation is also very important, that what are the elements of e to the power at. Also, if we know the eigenvalues, we should guess that what will be the structure of the e to the power at, and it will be helpful us to determine the stability of the system. And we have discussed the computation of e to the power at using Cayley-Hamilton theorem also. So in this case we have taken a example where we have seen that for particular this example we have seen that the roots are repetitive. If the roots are repetitive, then the elements, especially the off diagonal elements, that is here you can see the elements of the e to the power at will be in the form of t to the power l minus 1 e to the power lambda t, where l is the multiplicity in the eigenvalues. So here we have seen that two multiplicities are there, means two number of repetitions are there, so it will be the elements will be associated with that is 2 minus 1, that is 1, that is t into e to the power lambda t, where lambda is the eigenvalue. So now we will start to discuss about the properties of state transition matrix. So it is also very helpful to determine the state transition matrix some cases. So now first properties we can see, first property we can see, the derivative of e to the power at is equal to, mind that this e to the power at is a n by n matrix and the elements will be associated with the exponential terms. So if it is if we take the first derivative of e to the power at, so it is simply a into e to the power at, fine, or also we can write e to the power at into a. And here the proof is given. You can see that already in the last class we have established that e to the power at can be written in a infinite series, that is r equal to 0 to infinity t to the power r a to the power r by r factorial. So if we do the derivative, then it can be written r equal to 1 to infinity t to the power r minus 1 and r by r minus 1 factorial a to the power r. And if we assume that or we can write this equation, that is a into r minus 1 to infinity t to the power r minus 1 by r minus 1 factorial into a to the power r minus 1. And if we assume that j is equal to r minus 1, the same series can be written a into j equal to 0 to infinity summation the t j by j factorial a to the power j, and which is by definition is e to the power at. So we can write a into e to the power at or e to the power at into a. So now subsequently I will show you the another property, but I will not going to prove that one. So if you are interested to know how the properties have come, then you can go through any standard book. So the next property we will discuss, that is if we have e to the power a t1 plus t2, which can be written e to the power a into t1 into e to the power a into t2, which is very easy to verify. And then e to the power at is always invertible. That is very important. E to the power at will be always invertible. And how can you find out the inverse of that e to the power at? It is very easy. If we follow, then we can understand that e to the power minus at can be written e to the power at whole of minus 1, or we know that it is indicated by phi of t, that is e to the power at, okay, e to the power which is indicated by e to the power at can be written e to the power minus at of minus 1. Okay, so what is e to the power minus at? E to the power minus at will be the phi of minus t of minus that is inverse of e to the power minus t. So now you can see from this relation that if we want to write phi of minus t, that is equal to phi inverse of t. So it means that if we want to calculate the inverse of e to the power at, simply in place of t we should write minus of t. For example, I can show you from here. Suppose here this is the e to the power at and it has been asked, so which is actually phi of t, fine. So now it has been asked what will be the phi inverse of t. What would be the phi inverse of t, which can be easily calculated. Phi inverse of t will be equal to phi of minus t. So if it is a phi of t, then it is very easy to calculate what will be the phi of minus t. T will be replaced by minus t and you can get the inverse of e to the power at. So this is the way you can calculate inverse of e to the power at, which is always existing, okay, or which will always exist. So now the property 4 is saying that that phi of 0 is equal to a to the power a into 0 always will be a identity matrix. That is also a very important property by which when you are going to compute the e to the power at and the result is correct or not, it can be verified easily. Okay, so suppose it can be verified. Now here you see the for example this example, if we take suppose e to the power at, so now it is telling that e to the power, so if it is phi of t, if we will assume, then it is telling that phi of 0 will be e to the power a into 0 always will be identity matrix. So you just verify. For this example, if you put t equal to 0, so first you are getting 2 minus 1, that is 1. Here it is 0, it is 0, and this is 1. So it is the identity matrix. So you can verify for other examples also. Suppose in your exam it has been asked to calculate e to the power at, then suppose you have derived the result. So for whether the things are correct or not, at least you can check that whether e to the power a0 is identity matrix or not. Okay, so we have other use of this property also. Just in this discussion I'm going to establish, or I'm going to show that one. Okay, then if we want to compute the nth order of phi of t, so it is simply to calculate phi of nt. Fine. So if in your exam, if it is coming, suppose compute phi square of t, so better you should calculate phi of t. Okay, and then you should replace that t by 2t, so you will get the nth order or second order of or square of phi t. Then phi of t2 minus t1 into phi of t1 minus t0, okay, will be equivalent to phi of t2 minus t0, or it can be written phi of t1 minus t0 into phi of t2 minus t1. Now another thing here we can observe, which will be useful later on. Suppose if we want to calculate, suppose this is the phi dot of t. Okay, phi dot of t. Now if we want to calculate phi dot of 0, what will be that? Because e to the power, so it will be a into e to the power a of 0, and just now we have computed e to the power a of 0 is identity matrix, so it will be basically a matrix. So phi dot, if you compute at t equal to 0, you will get the a matrix. So this property will be useful very soon if we want to calculate the e to the power at. We will use this property very soon. So now, after discussing the properties, we now interested to know the rest of the things, that how we can find out the solution of non-homogeneous state equation. Previously only we have found the solution of x dot is equal to ax. Fine, x dot is equal to ax, and we have seen that the solution is xt equal to e to the power at x of 0. Okay, now we have the state equation x dot t equal to a into xt plus b into ut. Fine, and definitely here the xt belongs to Rn, and also we have the initial condition x of 0. Fine. Now this state equation can be rewritten as x dot t minus of ax, that is equal to b into ut, and now we will multiply both sides by e to the power at. So now we will get e to the power minus at into x dot t minus axt equal to e to the power minus at b into ut. So which can be written, that is d dt of e to the power minus at into xt is equal to e to the power minus at into b into ut. You can verify if you take the derivative, first derivative of this two term. Okay, then what will happen? If you keep first e to the power at fixed, e to the power at is fixed, then you will get x dot of t. Fine, then minus that we will get the derivative of e to the power at. So it will be basically minus a into e to the power at, okay, into the xt will be fixed. Okay, now if you take e to the power at common, so you are getting x dot t minus a into xt. With that, the e to the power at is multiplied, and this side will be as usual. Now what we will do, we will integrate both sides from 0 to t. So if you integrate both sides, so it is already the derivative, so if you integrate it, it will be as usual, that is e to the power minus at xt, and we are doing the integration limit is 0 to t, so we have to put the values from 0 to t. Okay, and this side, as we are going to take the derivative with respect to, sorry, integration limit is 0 to t with respect to dt, so that's why we will replace the t by a dummy variable tau. So that's why we have written 0 to t e to the power a tau b into u tau d tau. So tau is the dummy variable. Now you can see that we can pre-multiply the both side by e to the power at to have the x of t. Fine. So now if you put here the value lower limit and upper limit, what you will get? So it is basically e to the power minus at x of t, that is minus of, if you put 0 here, so it will be x of 0 is equal to integration 0 to t e to the power minus a tau b of u tau d tau. And from here, if you write the x of t, then we can write e to the power at x of 0 plus 0 to t e to the power a t minus tau b of u tau d tau. So this is the very important formula, that the solution of a state equation which is non-homogeneous. So x of t is equal to e to the power at x0 plus 0 to t e to the power at minus tau b of u tau d tau. Thus we have assumed that the initial time to be 0. If however the initial time is given by t0 instead of 0, then the solution of the equation must be modified at xt equal to e to the power at minus t0 x of t0 plus integration t0 to t e to the power at minus tau b of u tau d tau. So this equation you have to remember, because frequently in your exam it is coming to solve a state equation which is non-homogeneous in nature. Then this equation will be useful. Fine. So now the same thing, the derivation what we have seen here, that if a state equation is given to you which is non-homogeneous, how you can calculate the solution in time domain directly by the equation this as well as this. The same thing you can perform using Laplace transform approach also. That is also I am going to show. Suppose you have the state equation x dot t equal to a into xt plus b into ut. Now if you take the Laplace transform, then ultimately the x of s you can write, that is si minus a inverse into x0 plus si minus a inverse b into u of s. This expression already we have seen. Now if you take the inverse Laplace of this equation, then we can write x of t is equal to Laplace inverse of si minus a inverse, which is e to the power at into x0, and here you see the two frequency domain terms are multiplied. So basically you will get, means it is basically Laplace inverse of si minus a inverse, okay, that is convolution Laplace inverse of u of s. Okay, so that's why it has been written, that is e to the power at, b is a constant matrix, so e to the power at into b convolution of ut, and we know that from the definition of the convolution, then we can write x of t in the form of that e to the power at x0 plus integration 0 to t e to the power at minus tau b of u tau d tau. So the same expression we are getting what we have derived earlier with some different method. So now here another thing is that the e to the power at also can be written in the form of phi of t. So the same thing has been written in the next equation. Fine. So this is the way we can find out the expression of xt. So now if we want to compute the xt for a given input, so we have to use this equation to evaluate it. Okay. So now here if you see the expression of solution, state solution, then it is very interesting to note down that the first term, if you consider the first term phi t x0, okay, phi t x naught or x of 0, that is called actually, that is zero input response. Okay, so it is called zero input response. So here it has been given the explanation. Notice that the first term on the right hand side of the equation is the response due to the initial state vector x0. Notice also that it is the only term dependent on the initial state vector, because you see this term is also only dependent on x0, but next term is only dependent on input. Fine. So that's why, and we know that the initial the variables for which the initial conditions are required to be known are known as state variables. So that's why the response is called zero input response, since it is the total response if the input is 0. And the second term, if you see, that is 0 to t phi of t minus tau b of u tau d tau, it doesn't depend on the initial condition, it depends on the input. So that's why it is called zero state response. Okay, the second term called the convolution integral is dependent only on the input u and the input matrix b, not the initial state vector. We call this part response the zero state response, since it is total response if the initial state vector is 0. Okay. So we will, whatever the theory we have discussed here to compute the solution of a non-homogeneous state equation, we will try to verify with an example. Suppose the same example what we have taken as a homogeneous case, means only we have computed e to the power at, or the solution for this part x dot t equal to 0, 1, minus 6, minus 5 into x. Now a input term is also given, that is b into u, y equal to cx, and where ut is a unit step input and the initial condition is given 0, 0. So already we have computed, because you see we have to compute the solution with this equation, that is xt equal to e to the power at x0, that is 0 to t e to the power at minus tau b of u tau d tau, or by this equation. And previously already we have computed phi of t. So now from this expression it is very much clear that we have to compute e to the power at, then only we can compute xt, and after that certain calculation we have to do. So first, if this kind of problem is given, your work will be to find out e to the power at. Fine. So now already it has been computed, so that's why I have written here directly. So this is the e to the power at, and I am calling this term as phi 1, 1. So basically this is a matrix having 4 terms, that is phi 1, 1, phi 1, 2, phi 2, 1, and phi 2, 2. Fine. So now if this is the e to the power at, now we will substitute here in the equation. So now xt equal to, that is e to the power at into x0 integration, that is phi t minus tau. So if we have the knowledge of phi of t, if this is the phi of t, then easily we can calculate what will be the phi of t minus tau. So that's why it has been written phi 1, 1 t minus tau. Okay, integration. So 4 terms are there. Then b is 0 and 1, u in time domain, that is unit step, that is 1 into d tau. And if you compute, because here you see that the initial condition x10 x20 is given 0, 0. So if you put here this is equal to 0 and this equal to 0, this term is going to be vanished. Fine. And if this is going to be vanished, and if you do rest of the calculation, that is it is a 2 by 2 matrix and it is 2 by 1. Okay, so ultimately if you multiply it, you will get a 2 cross 1 matrix, which is like this. Okay, and now only the thing is that you have to calculate these two integral to compute the x of t. Okay, these two integral you have to calculate. So now how to calculate this? So now we have the knowledge of phi. What is phi 1 to t? Fine, already we know. So now we have to only calculate what is phi 1 of t minus tau, and we have to perform this integration. Okay, so now you see x of t we have written, that is 0 to t e to the power minus 2t minus tau d tau minus 0 to t e to the power minus 3t minus tau d tau, because already we know that what is our phi 1 2. So this is the phi 1 2 and that is the phi. We have to take phi 1 2. Another component is what? That is phi 2 2. Very good. Phi, this is the phi 2 2. Fine. So t will be replaced by only t minus tau, and we will perform the integration. And here one important thing I want to mention, that we are doing the integration with respect to d tau, so we can break this and we can consider e to the power 2t is a constant. So only we have to perform the integration 0 to t e to the power plus 2 tau, okay, d tau, and that has been done. And we already put the limit 0 and t, and then we got the two components of xt, this and this. So this is representing x1 of t and this is representing x2 of t with the unit step input. And if you want to compute the output, you can calculate the output 1 0 into xt. So output expression will be like this. So this is the way you can calculate the solution of a non-homogeneous state equation, and you can also compute the output of the system. Fine. Okay, now we will use this solution of the non-homogeneous equation to establish a fact or establish a claim what we made earlier. Okay, which is very interesting, that if one claim we made earlier, if we can write a system in the state space in the form of x dot t equal to a into xt plus b into ut, yt equal to c into xt plus d into ut, where the initial conditions are indicated by x hat of 0, then it is a linear system. How we can prove that one? Okay, so to prove that one, we can understand that this is the system. Okay, so this is, you can consider a system, okay, where the inputs basically are ut and the initial condition. These are the two inputs will be present, x of 0 hat, and then you are getting the solution x. Once you will get the solution x, then you can multiply with c to get the y. That is not a problem. But thing is that you are giving the input ut and the initial condition, and the system is going to evolve, and you are getting the system states x. Fine. So if this is the case, then using the concept of the solution, how can we prove that it will be a linear system? Or other way, we can say that it is obeying the superposition principle. So how we will verify that one? And this is the way we can do that. We know that the system solution is xt with the initial condition, and the input will be the solution like this, that e to the power at x0 plus z integration 0 to t e to the power at minus tau b of u tau d tau. Okay, so now to show the superposition holds, we need to show that if the initial condition x01 hat and x02 hat produces response x01t and x02t respectively with 0 input. So first here you see we have the two inputs. Okay, so first what we will do, we will excite the system. First we will assume that this ut is equal to 0. One of the input is 0. Okay, and suppose we are giving the inputs, that is in terms of initial condition, that is x01 hat and x02 hat. Okay, so then what will be the x01 of t and what will be the x02 of t? So it will be simply from the formula, if there is no input, we know that e to the power at into x01 hat, and it will also will be e to the power at x02 hat. Okay, that has been told here. Fine with this. And now suppose we, and second case, what we will do, we will assume that next case we will assume that initial condition is 0 and we are exciting the system with inputs u1 and u2, and in that case we can compute what will be the system response, because at that time we will compute the zero state response. Okay, so if we are so say here I'm writing, so if we are now exciting by u1 and then u2, okay, so what will be the output for the u1? u1 will be integration 0 to t e to the power a t minus tau b of u1 of tau. Okay, and if we excite the system with u2, then you will get the response 0 to t e to the power a t minus tau b of u2 tau. Okay, so that the things has been told. So it is written in the next slide, but now we want to know if now the system is excited by the u1 plus u2 with the initial condition x01 hat plus x02, is the solution, is the response of the system, is the summation of all these four individual inputs, that is x0, x01 hat, x02 hat and u1 and u2. If it is, then we can prove that system is linear. So that's why you see, if we have only the x10 hat input, then this is the system response or system states, and if we are exciting x20 hat, then the system response is this, and definitely it is 0 input, so ut we have assumed 0. And next case, if the initial conditions are 0 and if we have excited the system with the input u1, then we can get the states like this. So here definitely the x hat of 0 is equal to 0, means initial conditions are 0, and if the same system is excited by u2, then we will get the x2 ut. Okay, now if now the system is excited by, that is x10 hat plus x20 hat, and the system is excited by u1 plus u2, then what will be the system response? Let us compute that one. That also we can compute using our formula, that is xt will be e to the power at. So this is the initial condition now, and this is the input now, and now if we write in the form of this, then we are finding that xt is the total response when these two initial conditions and two inputs are given. Xt is the individual summation of the responses, that is x10 of t, x20 of t, x1u of t, x2 of ut. So in this way we can prove that the superposition holds. Now so this is the way we can prove the claim, and now we are going to show you some certain examples. Another example I'm going to show where you can see that one system has been taken and it is excited by a unbounded signal, that is ut equal to e to the power t, and it has been asked that to find xt. And if actually in the normal way, the way which I have shown, you can follow that process, but we want to see what is e to the power at for this A matrix. That is our interest. So if we find the eigenvalues of this matrix, we are finding that it is s plus 1 whole square. So if we make equal to, means this is the characteristics equation, and to find out the eigenvalues, if we make equal to 0, then actually we are finding that s is equal to plus 1 and plus 1, means two repetitive roots are there and which are positive. And then we can guess what will be the e to the power at. It will be that t into, definitely the term t into e to the power t will be there. So if you compute the way what I told, that using Laplace transform approach, you see the e to the power at you are getting in this form. And here most interestingly you can see that all the exponential terms are growing, because you can see that the powers are positive. And why it has become positive? Because the poles are, or the eigenvalues are positive. And now if you compute the way the xt, here the steps are shown, you can follow easily. And if you see the final expression of the xt, then you are finding that none of the states are converging, both the states are diverging, because the e to the power plus t terms are present. Okay. So now another example I am showing you, where you can see the computation of e to the power at using the properties of e to the power at, that I want to show you. Okay, so here x dot equal to a into xt plus b into ut, x0 has been given, and it has been asked that if the ut is a unit step input, find the state transition matrix and solve for xt. So let us see that what would be the eigenvalues of the matrix A. And if we found that the eigenvalues are real and distinct, then we can write the general form of e to the power at, because we know that if the eigenvalues are real and distinct, what will be the e to the power at. So let us see that one. So here we are finding that determinant of si minus a equal to 0 is giving the characteristics equation s square plus 6s plus 8 equal to 0, means s1 equal to minus 2 and s2 equal to minus 4. So the eigenvalues are real and distinct. If the eigenvalues are real and distinct, so then e to the power at definitely will be in the form of equation 17. Some constant into e to the power minus 2t plus k2 into e to the power minus 4t, k3 into e to the power minus 2t plus k4 into e to the power minus 4t, k5 into e to the power minus 2t plus k6 into e to the power minus 4t, and another element will be k7 into e to the power minus 2t plus k8 e to the power minus 4t. So this is possible only when, and this form can be written only when the eigenvalues are real and distinct. Okay. Now if we able to find this k1, k2, k3, k4, k5, k6, k7 and k8, 8 constants, then we can find out the phi t. Okay. So now how we can find the constant k1, k2, k3, k4, k5, k6, k7 and k8. So we require basically 8 simultaneous equations to solve it. Fine. So then we will use the properties. We know that one of the property is that phi of 0 is equal to identity matrix. So if we will compute phi of 0 here, then we will equate it 1 0 0 1, then we get 4 equations, and that 4 equation has been written here. So if we use the phi of 0 equal to identity matrix, then k1 plus k2 will be 1, k3 plus k4 will be 0, k5 plus k6 will be 0, k7 plus k8 will be equal to 1. And we know that phi dot of t is equal to a into e to the power at, and then phi dot of 0 will be equal to a. Fine. So now what we will do, we will compute phi dot of t, which has been computed here, and we will compute phi dot of 0, and we will write another 4 equations. Okay, so this is the another 4 equation. Now what we can do, now at a time 2 equations we will take to solve the each of the constants. So here the hint has been given. The constants are solved by taking 2 simultaneous equations 4 times. For example, equation 19, if you take the equation 19 and the equation 24 together to solve the k1 and k2. So like that, if you solve k1 and k2, you will get the phi of t. So this is the way also the phi of t will be calculated using the properties of e to the power at only when you are finding that roots are distinct and real. Fine. So now rest of the things are as usual. So here you can see that we can compute, because our objective was not to calculate e to the power at. Along with that, we have to find out the solution, that is x of t. So we have to find out the components, that is first component, that is e to the power at into x0 in the expression we have calculated, and then the integral term also will be calculated, and if we add, then we will get the xt. So this is the expression for the xt, the way you can calculate it. Fine. And I will end with the last lecture where we want to actually know that e to the power at. So this is the x of t we have taken, whose a matrix is given, and if we find out the eigenvalues of this matrix, that is a square plus 1, means the eigenvalues are, so s1 and 2 will be equal to plus minus j. So if it is plus minus j, means the roots are, or the eigenvalues are complex conjugate. So if we will get complex conjugate, but real values are means real part is equal to 0. So if we will get this kind of system, you know that this kind of system solution always will be the sustained oscillation. But by the computation of e to the power at, whether we are getting that one or not, we have to verify. So that's why to compute the e to the power at, we have to calculate si minus a inverse, and then we have to take the Laplace transform, Laplace inverse of si minus a inverse, and we are finding that each of the term is coming like this, s by s square plus 1. Now if you recall, or it is some constant 1 by s square plus 1. If you recall the formula of Laplace inverse of sin t and cos t, exactly you are finding that for omega equal to 1, it is going to match. So the e to the power at will be the cos t sin t minus sin t and cos t. So this can be also the e to the power at for a given system where we are getting the roots are complex conjugate. Okay, so in general you can say that if we have the roots are a plus minus jb, okay, then you can say that actually we will get e to the power at, okay, and the terms of e to the power at, you can get sine, okay, sine or cosine of omega b or b omega t. Okay, so like that, sorry, b, not b omega, it will be bt, sine into bt. So in this way the terms will be there. So why these are repetitively I am telling that the relation we are establishing, that the pole locations and the e to the power at, because the elements of e to the power at will give you the results regarding the stability, internal stability of the system, which we are going to discuss subsequently. Okay, so I will stop here, and the next class I am going to discuss about the nonlinear system and how it can be linearized, and also we will give the definition of the equilibrium points. And here I want to mention that next lectures, okay, from the next lectures you will find that it is actually pre-recorded. So at the beginning the lectures number, what it will be said, it will be not matched, because till now we have covered, I think, total Up to this we have completed total 14 number of lectures. So 15th number of lectures already it was pre-recorded, so it will be uploaded very soon. So here I will stop. So where we have seen that again I am summarizing the things that we have seen: how to solve the state equations of the system with the objective to find out the time response, and another objective is there to determine the internal stability of the system. So subsequently we will see that how the how the solution of the system is playing a key role to determine the stability of the system. Thank you.